Classical Physics Tutoring Chapter 1, Section 3. Now, this section we talk about energy. Okay, so Newton's didn't talk about energy at all in his book. And as I said, classical physics made of three major components. One is Newton's law. Okay, another one is thermodynamic. So this is independent law. And last one is electromagnetic, Maxwell's. And actually modern engineering, like a civil engineering, mechanical engineering, electrical engineering, all the engineerings, the foundation is these three basic laws, and this is the basic law of the classical physics. It's not just Newton. Now, thermodynamics, they define energy, but here we kind of do introductory section of the energy, because Newton's mechanics use energy a lot. Actually, we need energy. We need to understand energy in order to deal with many mechanics given by Newton's law. So what kind of energy we have? We have a potential energy, and potential energy is like when you move, pick up the apple, bring it to the branch, you need a force against the gravity, and here its energy is stored. How can we tell? Because when we release it, it's drop and hit the ground and make a damage. So there are some potential energies stored. So it's just a height in the gravity field. It doesn't have to be gravity. Any kind of say the spring, you stretch, and this is also potential energy. And where the potential energy is stored in the spring, the elastic material can store the energy. That's potential energy. Okay, now kinetic energy is something moving. So when you shoot out some cannonball, initial speed is 28.28. So kinetic energy is given by this speed. Okay, now we have a heat energy. What is the heat energy? Heat energy is like inside molecule, this molecule vibrate, and also electrons also moving around. The speed of electron, kinetic energy of electron, and the molecule vibration. There are many different modes. You know, this in this case, these atoms, the get close and far, and this theta change around, or its spin, or the bond distance change around. Okay, so basically molecules kinetic energy is heat energy. Okay, so chemical energy is like when you break this bond is possible, the potential energy field, this atoms here and this atoms here, and keeping certain bonding distance. If this atom get higher energy than this potential, bonding potential, then bond break and release the energy. So that's a chemical energy. And you have a nuclear energy. You know, the nuclear energy is like famous mc square. When the mass break into two mass, and the sum of two mass is not equal to m. It's rather slightly less. And what happened is there is a delta mass is lost. And lost, this mass is converted to energy. So actually delta m c square is the energy generated by this fission process. The atom break into two different atoms, that's a fission. Okay, and the fusion is m1 and m2. The small one is like helium. When it's combined together, it's the opposite equation. When it's combined, it doesn't become m1 plus m2. This is the fusion process. So some energy is generated by the lost mass. Okay, this is a fission process. So either way, it's mass is converted to energy, and that's will be covered in special relativity theory at the end of the classical physics. Okay, so there are many different energy, and important one of thermodynamics law is energy is conserved. That means when energy change from potential energy to kinetic energy, or other way around, or heat energy, okay, how it's combined, how its energy is converted, and after conversion, energy is always conserved. Total energy is same. That means this entire universe contains certain amount of energy, and that's never change. Okay, it's just conversion of energy types or form of energy. Okay, so that's one of important thermodynamics law, and you will learn this in more details in the thermodynamics section. Okay, but here we need to understand the introduction of the energy law to deal with Newton's mechanics. Now, potential energy, how we calculate potential energy is simple equation F dot dr, and what it is suppose you move this way and gravity force is this way, right? So gravity force and movement is dr. Okay, so it's a dot multiplication. That means only the component in the direction of force contribute, and the component sideway it doesn't contribute. That means when you have Earth and the satellite moving this way, so there's no potential energy consumption or gaining energy. It's the same as long as this distance is the same. Okay, when the satellite move further or closer, there will be potential energy difference. Okay, because this is the dot multiplication. So only the direction of movement it's count. Okay, so the potential energy for satellite, you take an integral, line integral, where you take integral because it's gravity is attractive force. If you get closer, then potential energy is less. Further, the potential energy is high. What is the highest? you have to go to infinite distance. Okay, so you can adjust when you take a integral. You have a c, and you can adjust the c to make it so that the infinite distance, the potential energy is 0, and all the potential energy here down to the planet is going to be negative energy. Okay, and that can be adjusted by this c. As you do any calculation of potential energy, this c is adjustable. Now, how about kinetic energy? Kinetic energy, we do some Newton's equation manipulation. The energy is like that, right? And since F equals m dv dt, we plug in here and we swap this, so it's become mv dv and 1 over 2 mv square. So this is a kinetic energy. Kinetic energy is speed v. When it's moving, speed v, and the mass is m, kinetic energy is given. And this equation is actually, you find out the approximation for the slower v, much slower than light speed. Okay, and that's you will see in the special theory of relativity. But here, definition is energy come from this. This is called work. And why? Why this is energy? Okay, you don't have an answer here. You will get the answer. Special theory of relativity, you will get the answer. The energy is redefined, and from this energy, you will see why this work is a kind of energy. Right now, you start with work. Work is energy. We start with this definition, and potential energy can be converted to kinetic energy. Okay, so another important thing is momentum. Momentum is very close to energy, mv, mass and speed. So it's got the same component in it, just slightly different quantity. So why it's different? Actually, they are the same thing. Okay, the different expression. Now that's come out again later, but since they are the same nature, the momentum also conserve. And how it's conserved? For example, momentum is a vector. Okay, energy is a scalar, and the scalar doesn't have a direction. The vector has direction information. Say if the mass m is moving at the speed v1 and v2 for the second mass m, their mass is the same. It's hit, then this impact causes exchange of momentum, and total momentum is equal to new speed. Okay, so the new speed after the impact, if you add up the momentum, it's same as the previous total momentum. And even the mass is different. The large one hit the small one. The most likely after impact, both still keep going. Or other way around, the smaller mass hit the large mass, the smaller mass may bounce back, and the large mass keep going. Okay, so this conservation of momentum you can see in Newton's Cradle, this toy. Suppose you give initial speed v and it's hit, then it's the same mass, so this one stop and lose entire momentum. Entire momentum momentum is transferred to here, and it's transferred here again, and transferred here again, and this one move up at the same height if there's no loss of energy. Okay, so it's just keep repeating. So this is a very good example of transferring momentum quantity. It's called Newton's cradle. So how do we know the new speed after collision? Suppose the V1 changed by delta V1, V2 changed to delta V2, right? So mv1 plus m1 m2 v2. Initially we had this much momentum. Okay, so it's going to be m1 v1 plus delta v1, the change of the speed, plus m2 plus v2 delta v2. This is v1 prime, and this is also v1 prime. Okay, we can write this way: m1 v1 prime plus m2 v2 prime. So unknown variable, we have two unknown variable here. So momentum is conserved here. If you simplify this, we'll get m1 delta v1 plus m2 delta v equals 0. So the momentum given by the first ball is going to be the momentum gained, right? Okay, now how do we know this? We have a two unknown parameter here. So we use energy conservation. It's going to be so this equation and this equation, we have two equations to solve for v1 prime and v2 prime, so we can find the exact speed after collision. Now, why collision? We call that impact exchange the momentum. Okay, that's in the Newton's equation. Say you have this Newton's equation, you take an integral on the both sides, then you get integral of force over time equals, here you go, this is momentum P. Okay, so momentum is, suppose this ball hit this ball, give F, the impact very short time, don't know how long, but very short time, then you get the reaction F. So the F delta T integral 0 to delta T, this short time force is going to be the P, which is the change of momentum, delta M delta V, no, delta P, yeah, because depend on this, depend on if it's M1 delta V, if it's M2 delta V2. Okay, so the exchange of momentum come from this action reaction. You get force, you also get the force. You give a force, you get the force. So the delta P is exchanged here. Okay, that's in the Newton's equation. The action reaction law guarantee that exchange is equal. Whatever you give, you receive, which is delta P. And depend on the weight, delta V, the speed difference, is going to be different. Okay, that's the cause of impact, the momentum exchange. So exchanged by impact, and actually this one is called impact. Okay, there are many applications for that. For example, suppose there is an explosion and you have many pieces scattered around. Okay, how do we determine where the explosion happened? Say explosion happened here. Every pieces were here, concentrated, and it's scattered around, right? So from this distance we can tell initial speed. So V1, V2, V3, all the pieces we put together, initial speed. Then we can tell the location of this explosion and what was the explosive power, energy level. Okay, so there are many ways to apply this knowledge of Newton's impact and momentum and others. Okay, so I hope you enjoyed this video. If you like, please subscribe and move on to the next section, which is angular motion or circular motion.